Good day, everyone. In our previous lessons, we learned that when a particle travels in a spherical motion, there are two kinds of angular momentum that can be produced. We have the orbital angular momentum and we have the spin angular momentum. We discussed the orbital angular momentum and we found out that it is a kind of an operator. In quantum mechanics, we are very much interested of having that operator because any operators that acts on a wave function, it produces an eigenvalue multiplied by that eigenfunctions. This means to say that for a given operator, we let that operator acts on that wave function and we can calculate the eigenvalue. From the calculated eigenvalue, we can also derive the eigenfunctions. So therefore, we are interested of knowing that kind of operator. So since orbital angular momentum is an operator, then in our previous lessons, we derived the components of the orbital angular momentum in terms of spherical coordinates. And we also learned that the square of that orbital angular momentum is compatible to all components of the orbital angular momentum, which means that the component, any of the component of the orbital momentum and its square of that orbital momentum shares with the same eigen functions with different eigenvalues. So therefore, we can describe the system if we have two kinds of operator that are compatible. We we use the ladder operator in order to derive the levels of the eigenfunctions. So we are deriving all the operators in orbital angular momentum. In this video, let us now discuss the spin, the second angular momentum, and we focus on the spin one half. This is Marlon F. Sasidon from the Visayas State University, Baybay City, Leyte. Now, as I've said, when a particle travels in a spherical motion like the hydrogen atom, so electron orbits around the nucleus, and there are two kinds of momentum. We have the orbital and we have the spin angular momentum. In in classical mechanics, the orbital is the cross product of the position cross or the dot cross product with the linear momentum. But another another momentum is we have the spin, which is the product of the moment of inertia and the angular acceleration, angular acceleration omega. And this is associated with the center of mass. So as the particle, as electron rotates around the nucleus, we have the orbital angular momentum, and at the same time, that electrons rotate about its center of mass. So we call that as a spin, just like Earth that rotates around the sun. So while rotating, it rotates also around with respect to its axis. But in quantum mechanics, uh, we have actually a similar behavior of the particle that rotates around the circle. So therefore, we have also the orbital and we have the spin angular momentum in quantum mechanics. Now, the spin is actually a carbon copy of what we did in our orbital angular momentum. So we use also the commutation relation. So therefore, understanding about the orbital linear momentum and studying about the spin, it is not quite easier because we have already the idea on how to find the operators in spin. So take note that previously we derived all the operators in orbital uh, angular momentum, including its ladder operator. So in this topic, we will also do a carbon copy what we did in orbital momentum. So for example, uh, since spin is an operator, so we have also the x component, the y component, and the z component of spin. Now the commutation x, sx, and sy is I, its bar is z. So this is similar to the orbital angular momentum. So if we will derive this one, we use the commutation relation and will arrive this kind of value. Now for is y and is z, then it is equivalent to I its bar is x. So it's a kind of uh, cyclic rotation. So we have x, y, and we have z. So if we started y, we have z, and the next is x. Okay, so therefore, for is z and is x, we have I its bar is y. If we reverse it, then we can notice that negative. We have the negative value. If we reverse x, y, and we have yx. And also the zx is z and is y, we have the negative h bar is x. And also with x, the commutation of x is x and x z, h bar is y. Okay. Now as I've said, this is a carbon copy in orbital angular momentum. So we can say that the components of the spin did not commute, meaning they are not compatible. But the square of the spin is commute with x. So the result should be 0. And also the s squared and sy commute also with x squared and sz. It should be equal to 0, which means that the square of the spin and x are compatible also with xy and with is z. So if they are compatible, then in quantum mechanics, these shares they have the same, no? They share with the same eigen functions, but of different eigen values. Okay, so the this relationship we can be derived using our previous knowledge. Okay, so again, is squared and is z satisfied, meaning they are compatible. So therefore, it satisfies that if that is squared acts on a state wherein we have now is and m, where is the spin, m is another quantum number, and this it is equal to the h bar squared times the s plus 1 times the state or the state vector or the eigenvector of in terms of is and m. Okay, so we have the operator a squared that acts on a wave function or on an eigenfunctions, then it provides an eigenvalue. And the eigenvalue is its bar times is plus 1. This is again replicate with the orbital angular momentum. In our previous, we have L square that acts on the harmonic uh, function, which is the uh, angular function in terms of L and M, and it is equivalent to h bar L times L plus 1 times the eigenfunction. So in spin, we have this is represented by uh, spin, and Sm again is a state vector, and it depends upon the spin and the value of m. Okay, for Sg, the Sg acts on the same state because they are compatible to each other, so they must share with the same eigenfunction. It has the eigenvalue of h bar times m multiplied by the state vector. Okay, so let this be equation 1. So take note that s will start at 0, and we have 1 half, 1, 3 halves, 2, 5 halves, and so on and so forth. So you just add 1 half, then that's it. Then m is actually depends upon the value of s, and it starts with a negative s and it ends with s. So m will depend upon the value of spin quantum number. M is another quantum number. Okay, so take note that in previous problem 4.2 in the book of Griffiths, we have the lowering and raising operator. Now the when the raising operator acts on the harmonic wave function FL M, it is it, meaning if we let the raising operator acts on that wave function, then it levels up with one higher, 1 degree, or one. You have to move to another level. So it is now become FL m plus 1. And we have this eigenvalue, or this coefficient is h bar times the square root of L plus 1 minus m plus 1. We derived this in our previous lessons. Okay? So it is also equivalent to that. H bar square root of L minus m times L minus m plus m plus 1. Then we have F L, and this time m was added by 1 because you let the raising operator act on that wave function, so it moves to the next level. Okay, now if we apply the lowering operator on the same wave function, then the wave function now will decrease to its level, so it move and a lower level, so it should be m minus 1, and we have that values. Okay, so we have h bar square root of L plus 1 m. Then we have the L minus m plus 1. And take note, we have this negative 1 because we apply the lowering operator. So these are what we did in our previous lessons. Now, in a spin angular momentum, in the basis of m and s, again, s is an spin, m is a quantum number in magnetization for m. So, but m, remember, depends on the value of the spin. Okay, so if the orbital has a raising operator, then spin should have also a raising operator, and it represented by is plus. And this is plus acts on this state vector, which is a function of or depends on the spin quantum system, quantum number, and we have this m quantum number. And it should be h bar multiplied by square root of is plus 1 minus m times m plus 1. And we have this is times, we have this m plus 1. Okay, so therefore, we can also simplify this, or we have this equivalent value, and again, this will move to add on, no? So is m should be increased by 1 because we apply a raising operator. So m should be added by 1. So this is just the same on this part that we add it 1. Then we have this state vector m plus 1. Okay. So similarly, in a lowering operator, we have this uh, s negative that acts on the state vector, Then we have this value. Then we have to reduce the value of m by 1 because we let the lowering operator act on that state. So the state should lower also. And simplifying this, we have this result. Take note, we have this h bar square root of s plus 1. Take note is minus, while this one is plus. And we have s minus m plus 1. And we have this is spin, and we have the is a minus 1 because we apply the lowering operator. Okay, so again, the derivation of this are can be found in the previous topic. So therefore, the combination of the two, the lowering or raising operator, will result to this value. So therefore, we are now aware that we have this result if we apply a raising and lowering operator. If we apply a raising and lowering operator on a state vector, then we can provide this result. And it depends upon the value of S and M. Okay? So take note that the lowering and raising operator is equivalent to Sx plus or minus I is Y. So this is the same as what we did in orbital angular momentum. But this time, the difference of this is the orbital angular momentum is a kind of spherical harmonics. The wave function, the eigenfunction is a kind of spherical harmonic. Why? It's because the orbital angular momentum depends on uh, the simultal angles and also uh, the orbital angles. So therefore, the wave function should be a spherical harmonic. But the spin is not a spherical harmonic because spin does not depend on the angles, the the polar angles and the uh, azimuthal angle. Okay, so uh, the spin, the wave function, the eigenvector of the spin will depend upon the spin L, the spin S, and also the value of M. Okay, so that's it. Okay, so the S value will vary depending on the material. So in pi meson or pion, the spin is 0. While electrons, the spin is 1 half. Protons have spin 1. The delta baryons, up or down quarks, have a spin of 3 halves, while the graviton, like protons, carrier of the gravitational field, have a spin of 2, and so on. So what does it mean? That any particle have corresponding spin. We have spin 1 half, we have spin 1, we have spin 3 halves, and so on and so forth. Okay? Now, the is that has a fraction like 1 half, 3 halves, 1 half, 3 halves, 5 halves, those are this is the spin of the particles for electrons, neutrinos, quarks, protons, neutrons. So the spin numbers or is are in terms of fraction. While while in photons, the Z plus minus, the W plus minus, or you have the Z, the gluons, and other particles, we have the spin of a kind of integers. So 0, 1, 2, no fraction. Okay, so there are two kinds of particle. So they are categorized into a fractional spin, and we have the non-fractional spin. So the fractional spin, we call it as fermions particle, while the integers are bosons. Okay, so we have the fermion particles and we have the boson particles. Okay, in contrast, in orbital angular momentum, or L, for an electrons, hydrogen atom, okay, takes only any integer value, okay, and will change from one another when the system is perturbed. But is fixed for any given particle. That this makes the theory of spin comparatively simple. So spin is kind of fixed value. Okay, so we have this problem taken from the book of Griffiths for 4.28. Problem says that if the particle electron kuno were a classical solid sphere, if electron were a classical solid sphere, so it's in classical system with radius of RC, radius of that is electron square over 4 pi permittivity times the mass of that electron times the square of the speed of light. So this is now the so-called classical electron radius. This is by assuming that the electron mass is attributed by energy stored in its electric field. This is via Einstein formula of the popular formula, the E is equal to mc squared. Now, if the angular momentum, let us say, one half of the h bar, then the question is how fast in meter per second would a point on an equator be moving? Another question is, does this model make sense? If we have that kind of radius, it's that makes sense. So we have to investigate that. Actually, the radius of the electron is known experimentally to be much less than RC. But this makes matter worse. But this okay. So first thing to do is we will answer how fast is that, okay? And we will notice the answer if that's we will examine the answer if that's realistic in 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 the actual value. So to answer this problem, first is take note that the orbital angular momentum is the product of the moment of inertia times the angular acceleration. So the angular momentum L is already given by one half its bar. And take note that the sphere the sphere we have the moment of inertia of a sphere. So moment of inertia is a kind of physical quantity that quantifies the amount of rotation, okay, within its material about a certain point of pivot. So in spherical, with respect to center, we have we have that moment of inertia. Okay. So in that case, okay, so in order to solve this, remember that the angular frequency is a function of velocity, and we are to solve for the velocity of the particles. Okay, so this is now with respect to z, no? So we focus on z. So Lz is equal to I times omega z, the angular acceleration with respect to z. So the rotation now is actually the rotation is with respect to z axis. So if we have x axis, y axis, then z axis, then it revolves around the z. Although we can also use z, x, and also y respectively. Okay. So now take note that this one half its bar is the angular momentum. So it should be Lz should be its bar over 2. While the moment of inertia in geometry, it is equivalent to, for a circle, it is equivalent to 5 halves of times the mass times the square of the radius. Okay? So therefore, uh, this is now the moment of inertia. So you can recall this in your geometry or in a previous topic, the moment of inertia of a circle with respect to, so if this is the circle, then with respect to that, the moment of inertia is given as 2/5 of the mass times r squared. Okay? So, but remember, this angular acceleration is related to velocity, where in the linear velocity is the product of omega r, which means that the omega is equal to b over r. So therefore, this angular frequency is equal to velocity over the radius. Okay? And we are interested to solve for b. So solving for b, supply, take note that this we have its bar. Its bar is actually in terms of the Planck's constant. So 2 pi. Then we have this mass of electrons, and this one is given in the problem. So therefore, the only unknown is V, and it should be, by calculations, this is 5.13 times 10 raised to 10 meter per seconds. Okay, look at this. Is this realistic result? Now take note that this is much greater than compared to the speed of light. The speed of light is just equal to 3 times 10 raised to 8 meter per seconds. And this velocity is the velocity of what? The velocity of photons. Okay? A massless particle. So if we have a particle that don't have mass, then it can travel through in the speed of light, which means that the speed of light is the ultimate velocity, the highest velocity of all particles. Why? Because it is a massless. Now, this result shows that the electron is, it has a velocity of 5.13. And remember that the electron has a mass. So meaning, it cannot compete with photons. Meaning, it is impossible to reach the electrons, its velocity equal or greater than the speed of light. Because only the photon particles or the photons can travel up to the speed of light. So meaning this one is, this velocity is not realistic. Okay? Because it is much greater than the speed of light. Okay, so what does it mean? So meaning to say that the radius, this is the given radius is just for classical system, and we cannot adapt that in a quantum system. Okay, so that's it. Okay, so the model don't make sense in short. Now let us now proceed to the spin one half. By the way, this is 4.4.1 of the book of Griffiths, and this is spin of one half. So let us focus on the spin of one half. Take note that in a particle there are different spin. We have zero, one half, one, and so on and so forth. Okay, now this time we have this one half. So let's disregard the other spin. So let's focus on one half. Why spin one half? Why we focus on the one half spin? The reason is uh this spin, this is actually common to the ordinary matters like protons, neutrons, electrons, as well as quarks, and all leptons. It has the spin of one half. So meaning, uh, given this spin is one half, there are a lot of particles that we can analyze. Of. Okay. Now, this idea can be extended to three halves and so on. Take note, this is one half means it's a fermion. So these are particles in fermions. Okay. There are, meaning in that case, since we have only is one half, then there are two states. Okay, of the state is M. What does it mean? We have only two states for one half. For is one half. What are they? We have the state one half and one half, meaning is one half, is, and this is M. So remember, since is one half, then our M is only negative one half and positive one half. So there are two kinds of state we can provide. Okay. So, and remember, m depends on the value of s. Since the value of s is one half, then it starts with negative one half, and the next line is one half. So we have the two kind of states. So first state, we have this one half, one half. Mean s is one half, m is one half. Remember, two values of m. We have negative one half and one half. So this one is here. We have the one half, and we have the one half, negative one half. Okay? Or for simplicity, we can use the symbol. The arrow up means spin up. Okay? The arrow down means spin down. Okay? So spin up and spin down. Then these are the vector bases. These are the two eigenstates in terms of we have this basis. Okay? Now the general state, let us say psi uh, of spin one half. Particle can be represented in two elements of the column matrices, column matrix or spinor. So the term of the two elements in a spin one half, we call it a spinor. So if we let psi be equal to a two element, let us say A and B, we don't notice A, we don't notice B. So A and B represent the elements of the matrix. So it can be written in mathematical statement as psi is equal to A times A sub x means uh, the spin up plus the B. By the way, this is B. No, this is B, sorry. This should be B times A uh, psi 1 minus, meaning spin down. Okay, or the spin up is a kind of matrix. We have this kind of x plus we have this element 1 and 0. So this is now spin up, okay? And we have this spin down. So psi plus spin up, psi x, psi minus is spin down. Or this can be written for simplicity. We have the a sorry, this is again b. Sorry, this is again a. This is b. Okay. So then uh we have this spin down, spin up, and spin down. Uh, column matrix, two elements, column matrix. So meaning there are two ways to present the general state side, spin one half. So we have the option to use this one, or you may use this, wherein this one is the spin up, while this one is a spin down. Alternatively, you can also represent this side with we have this A times the spin up plus B times spin down. Where again, the spin up again is in the two elements column. And we have this down, spin down. Okay? 0 minus the spin down. 1, 0, spin up. Okay. Now, as I've said, in spin or angular momentum is just like what we did in orbital. So we are also interested what is the operator squared. So we are very much interested on what is the value, no? What is the value of that operator? Because if we have that operator, we can now let that operator act on the wave function or the eigenfunction, and it can now provide the eigenvalue times that wave function. So if we have that operator that can act with the eigenfunctions, then we can describe the system using that operator. So the question now is, what is a squared? Then after this, let us also derive the operator of the spin, the x component, the y component, and the z component. Along the way, we also use derive the ladder operator in preparation to we have the raising and lowering operator in order to derive the eigenfunctions in different level. Take note that if we have the raising operator, if we let that raising operator act on that wave function, then it levels up by one level, and so on and so forth. Remember, levels are discrete level, because energy is also a discrete value. Okay, so the question is, what is a squared? Of course, this should be in a matrix. No, it should be in a matrix representation, or it can be in mathematical representation. It can be 2 by 2 column, or it can be a 3 by 3, and it depends upon the tree. But since we have spin one half, so there are two kinds of elements: first element and second element. And most probably, this is squared is actually a 2 by 2 matrices. So what are the elements of this matrix? So those are the questions that we need to answer. Okay, recall that the L square in our previous lessons were derived, and we come up with negative h bar times this element. This is in terms of the spherical coordinate, spherical coordinates. So what is now the equivalent? If this is L square, what is now A squared? So those are questions. And of course, since is does not depend on the angle, then what should be the value of the A squared? To start with, let us again use the equation 1 that we derived previously. When this is again coming from this is pattern to our previous topic in orbital angular momentum. So we have the operator acts on the state, then we have this result, and it levels up. No, we have this eigenvalue, and this is now the state, the same state. So A squared, and we have this Z squared, and it provides an eigenvalue of its bar M. Okay, so this is again pattern with the orbital angular momentum. So for S one half, now we can now substitute the values to any of that things. Okay, so for example, A squared. Okay, so if we let this A squared operator act on this uh, racing operator, this is racing, remember. This is racing, this is spin up state. It is always equal to its bar squared. So this is its bar square. And yeah, we have ace is one half. So we have this one half. Then ace is one half plus one. Then we have this again, the same is value. So remember, we have this eigen state, and this is also the eigen state. Okay, then simplify further, then we have 3/4 of its bar square, say spin up. Okay, then let that be equation 3. Okay, now if we let that a squared act on the lowering operator, then of course substituting that to this one, so if we have the same value. Okay, then simplify further, then we have that result. Of course, they are almost the same with equation 4, equation 3, but the difference is we have this spin down. Okay, then take note that, as I've said, since our spin is one half, then we can produce only a maximum of 2 by 2 matrices, matrix spin of the operator is. We cannot provide 3 by 3 because we have only spin of one half. And there are two kinds of state that we can produce, the negative one half and we have the positive one half. Okay, so let that for 2 by 2 matrix represented by is D, E, F. So first element, second element, third element, fourth element, quorums and law. So we have this E squared. So using is equation 3. So if we substitute this E squared, substitute it here sa atong equation 3, then of course this will be the answer. So equation 3 we have h square, then substitute it with this one, the 2 by 2, and this one is our spin up. Take note, 1, 0 is a spin up, and this is 3 halves in equation 3, it's bar square, and this is our spin up again. Okay, so what's the result? After that, okay, so simplify, take note in linear algebra, this can be multiplied, this coefficient can be multiplied with here and also this one. So this is 1 times 3/4 times h bar squared, and we have this result. While the next element, which is 0, because 0 times any number is 0. Now, what does it mean? It's meant to say that this C is equivalent to this one, while E is equivalent to 0. So therefore, it should be, we have now the value of what? We have the value of C and the value of E. Now the question is, what is D and F? So with that, we can use equation 4. So we will follow the same procedure that we let this A squared act on the lowering operator. So remember, this one, the A squared act on the raising operator. But this time, equation 4 act. We let that act on the lowering or lowering operator. Oh no, spin down. We This is spin up, and we have now this time spin down. Okay, so again, multiply, then we have that result. Also, okay, again, this also we have to you have to review the matrix multiplying 4 by 2 by 2 by 2 by 1. So this should be 1 times C unya 0 times D. Add the two, so C plus 0, the answer is C. Okay? Now this time, 1 times E added by 0 times F. So you have to add the two. Now if you multiply the 2 by 2 by 2 by 1, then the result is a kind of kinetic matrix. So we have this one column with two rows. So it should be C and E. Okay? Now, similarly, in this case, multiply C times 0 becomes 0. And yeah, we have this, we have this 1 times D. So it should be D. Okay? Then 0 times E, sorry, plus 1 times F times 1. So we have this F. So we have this D, F. Again, we have this 2. Then a matrix algebra again. This is D is equal to 0, while F is equal to 3/4 of its squared, its bar squared. So we have this result. Okay, so we are already uh, completed with the value. We have the value of C, the value of D, the value of A. We have the value of F. So substitute that results. Then, of course, we can reduce this matrix by factoring, di ba? We can take factor of this. And in linear algebra, it is equivalent to E squared is 3/4 h bar, and we have this 2 by 2. We have 0, 1, 0, 0, 1 matrix na 2 by 2. Okay? So this is now what we are looking for. This one. This is the E squared operator. And that is 3/4 h bar square times the 2 by 2 matrix 1, 0, 0, 1. Okay? So therefore, this is now ready to uh, act. So if we want a wave function, then we let this operator squared acts on that wave function, then there is a corresponding eigenvalue and also corresponding eigenfunctions. Okay? So this is only for squared. Now next question is, what are the operators? The x component, the y component, and the z component. And that will be the next. So the next is operator is z. So you again, we are interested with z. So let us start with z. So the operator is z. What is that? What is the equivalent of that? If the squared, if a squared is we have the result previously, what is now the component of the spin along z-axis? In previous topic, in linear or orbital, we come up with this. The z component is negative h bar partial partial of p. So this we derived this in previous. Now this time we are now interested to have this one. Again, this is operator, so this should be identified because all operators can provide eigenvalues. And remember, it is a kind of what measurable value. So like operator which is Hamiltonian operator that acts on the wave function, then we have that energy which is the eigenvalue of E. So we can solve for E in Schrodinger equation. So again, what is how to derive the is component of operator, the Z component of the spin operator. So we start again with this one, equation one. So then for S is equal to one half, take note. Again, for S equal to one half, we have two values of M. We have one half and we have only, so we have only two values of that. Okay? Then substitute that here. Previously, we work on A squared, but this time we will work on this. So is Z and we have is M, eigenstate, where A is one half, and it can be, M can be one half, or it can be negative one half. Okay? So we have this H bar M, which is the eigen function, times the same state is M. Okay? So using these values, apply that, okay, we will let the Z component acts on the spin down, spin up, and we have this again, one half of its bar. Okay? Then we have that spin on half. Okay, equation 5. So then we can also let that Z component acts on the spin down. Then we have negative one half its bar spin up. Equation 6. Okay. Then again, similarly, we have a 2 by 2 matrix spin for for the spin operator along Z component. It is a kind of 2 by 2. Why? Because we have only two values of is. If it is three values, then it is a 3 by 3 matrix, and so on and so forth. So let is Z be equal to of 2 by 2 component, which has a component of C, D, E, F. So therefore, we have this using equation 5, almost the same what we did previously. But this time, we are talking about is operator along Z. Then, substitute that value to the spin up, then simplify, same process of what we did previously. So we have that CE, then multiply again, follow the, you have to check your linear algebra. Okay? Then, with that result, it shows that C is one half of its bar, while E is also zero. Okay? Then using equation 6, same process. Let that operator is the operator act on the lowering operator. Oh no, spin down. Spin down. This operator is Z, act on the low spin down. So it come up with this, and we have this spin down. Then combine mathematically, then we have that. Then of course, D is 0. If is negative 1 half, it's bar. Okay, we have now the value of C, D, E, F. Then going back to this one, substitute the value of C, D, E, F. Then we have this result. Okay, then simplify, remove the common factor, and we have that each bar leave the negative sign. So we have each bar over 2, and we have this result. Okay, we have that result. And this is now the spin, the Z component operator. It's each bar over 2. Okay, so that's it. No. Then the question is, what is now LX, LY, and LY? How can we obtain that? Take note, this is only for Z. This is only for Z. Okay, but in order to solve for that, we have to use the ladder operator first. So, what is now the ladder operators? So, before going to solving for Sx and Sy, what is the ladder operator equivalent? So, recall that in orbital, remember we always refer the orbital. So, this is now the orbital in spherical coordinate. Okay, so raising operator plus lowering operator minus. Okay, now what is the equivalent ladder operator for spin? So again, we started with this one for the raising and lowering operator as is a. This is actually pattern again in the orbital angular momentum, and we have this result. Okay. Next is for S plus, meaning the raising operator of spin that acts on the spin up. What's the result? Okay, then substitute the value. Okay, so for substitute M 1/2 and S equal to 1/2, and the result is substitute the values here. Okay, substitute 1/2, 1/2, 1/2. Then we have this result. Then simplify, and the answer is 0. So what does it mean? That if we apply the raising operator spin to the spin up, then the result is 0. Why? Because we have only two values. It's spin down or spin up. So there is no other state above the spin up. So the answer is 0. Meaning we cannot find value. Okay. Then for is, if we let that raising operator acts on the spin down, spin down. What will be the answer? Okay, then mathematically substitute the values of is and m, and the result is, okay, we have is 1/2, and we have m is negative 1/2. This time it's negative. Okay, then apply, then the result is we have this result. Okay, meaning it exists. Okay, once you apply a raising operator to spin down, of course, we have another label, which is this one. Okay, and take note, what is this? This is actually each bar times the spin up. Okay, that's the answer for that. Now, if we apply the lowering operator now this time, so previously we applied the raising operator of the spin up and raising operator of spin down. What will happen if we apply the lowering operator to the spin up? Of course, simplify that values again, 1/2 for S, 1/2 for M, then substitute values, it come up with this one. So meaning it exists, of course, di ba? You apply lowering operator of the highest, which is the spin up, then there should be something below that line. And that is its bar. Then we have that uh, lowering spin down. Okay, that's the result. So take note, we have to remember this one, these values. This result this one, and also this one. Okay, next is apply a lowering operator to spin down. Then substitute. And of course, the result is 0. Why? Because if you apply lowering operator, the spin down, it does not exist. There's no result in that. Okay. So therefore, these are now the collections of the lowering and raising operator that acts on the spinors or the spin up and spin down states. Okay. So that's it. So this is now the summary of what we did the previous slide. So now for the spin operator, no, for the low racing operator, again it's kind of two by two. Okay. Then again for lowering operator is another two by two. So we have that. The psi is remember spin up, psi plus, and we have this psi minus the spin down. So this racing operator, which is this one, we have this, and substitute that plus psi plus, which is the spin up. Okay, then you can also substitute the lowering operator here. Then we can solve everything. So then substitute, then it should be equal to 0. Take note, this one, using this equation, we have this is raising operator in terms of matrix 2 by 2, and we have this spin up, and the answer is 0. That's according to this statement. Then simplify, then we come up, we can say that C is 0, then E is also equal to 0. Okay, now next, applying the substituting the values of the value of the pressing operator to the spin down, then we have that. Combining this 2 by 2 with 2 by 1, then of course you have to do the matrix algebra, multiply and add, then we come up with that result. And of course, D is equal to H bar, while F is equal to 0. So we have now these values. Then substitute the value. C is equal to 0. C is equal to 0. D is equal to H bar. E is equal to 0. F is equal to 0. So we have this result. Then we can notice, we can take out the constant common factor, and we come up that, and this, therefore, this is our racing operator. And the racing operator, so remember, each bar times the 2 by 2, 0, 1, 0, 0. Okay, now for the next equation, applying now the lowering operator on the spin up, which is this one, then substitute again the same process, then do the linear algebra simplification, then we can say that C is equal to 0, E is equal to H bar. Okay, then apply it again, but this time for the lowering spin down, then do the same process, then simplify further, and we come up with a D is equal to 0, F is equal to 0. Then substitute that values to the lowering operator, and we have this lowering operator in terms of the uh, H bar. Okay, and we have that 2 by 2 matrix. In racing operator, we have 0, 1, 0, 0, but in lower operator, 0, 0, 1, 0. So they are not equal actually. So in any time that we apply the racing and lower operator, we have to use this matrix. Also with xj and also with a squared later on. Okay. So what is now? Let's go back to what is xy and sx and xy. So to derive this one operator, again we use the ladder operator. Now before that, notice that in our previous lessons we derived this one for the orbital angular momentum. Now what is the equivalent for the spin angular momentum? Okay, to answer this is just simply use the definition of the raising and lowering operator. The raising operator is Sx plus I is Y, while the lowering operator is Sx minus I is Y. So therefore, we have that result, equation 7, and we have that equation 8. Okay? Now, look at 7 and 8. If you add the two, by the way, take note that the raising operator was already derived in the previous slide, and also the lowering operator. So we have now this is the raising, and we have this lowering operator. So we can now substitute this later on. Now, before that, look at 7 and 8. If we add 7 and 8, what do you think? We can, this will be cancelled out. Okay? The I is Y and I is, can be 0. Okay? Then we have that result. We have is plus, di ba? Raising plus lowering operator of is equal to 2 is x. Solving for is x, then we have that. Of course, 1 half. Then substitute this matrices, this one. Substitute this matrices. Raising and lowering operator. So add. Okay? So again, you can use your linear algebra. You can take this out, then combine these two. So you have to add this one, 0, 0, 1, 0, 0 plus 1, 0 plus 0. Then we have now a combined 2 by 2. And that's the answer. Okay. By the way, this time, multiply this 0 times this one, then that one, this set, yeah, 0, it's bar 0, it's bar. So we have this result. It's bar over 2. And this one is also it's bar over 2. Okay. Then add the 2. Add the 2. Then we have that. So 0 plus 0. It's bar over 2 plus 0. So of course it's bar. 0 plus it's bar. So we have this one. It's bar over 2. 0, 0. Yeah. Okay. Then take the common. Take out the common and we have this. So this is your x component of the spin operator. Okay. Now, we add 7 and 8 previously. Now, if you subtract this equation 7 and 8, then the result is that one. Okay? So we have now the presence of is x. Of course, previously, if you add, is y will be removed. But if you subtract, is x will be cancelled again. So therefore, we can solve for is y because take note, we have raising and lowering operator. Then, do the same process. Take note, we have the presence of I, 2i. So then, multiply this one, multiply also, then subtract the 2. So when you subtract, it should be 0 minus 0. H bar over 2i minus 0. 0 minus this one. So meaning negative. 0 minus 0, 0. So therefore, that's the answer. Okay? Take out the common in matrix algebra. Again, we have h bar over 2. And we have these values for Sx and Sy operator. Okay? So we're done. Okay? We are done. So therefore, this is now the summary. Therefore, we have is x. You have to memorize this. Is y. Okay? Then we have is z, previous. And we have these three components of the spin operator. Is x, is y, and is z. Now, take note that this one is 2 by 2. This is contains of 1. So we have this, let that be omega x. And this one, omega y. And we have that omega z. So, therefore, we have this 2 by 2 matrices, a unitary. Okay. And we call this as the pulley spin matrices. These are called as the pulley spin matrices. So if you multiply the pulley along x spin with its bar over 2, then we have this x component. So meaning, just memorize this, then multiply by its bar over 2, and that's it. It's already is x. Okay? So again, we have this Pauli spin matrices. The omega x, omega y, and omega z. So therefore, we can say that this is x is just the product of its bar over 2 and the Pauli matrix along x. While is y is h power over 2 times the Pauli spin matrix with respect to y and also with z. Okay? So the operators, again, take note. The operators x, is y, is z, and is r are all Hermitian. So Hermitian operators. So therefore, uh, we have the law, di ba? We have the process. If they are Hermitian, then mostly of the operators are Hermitian. But again, is x and is y are not compatible with also with z. But these components are compatible with a squared. So that's why we have the two combinations. If you want to solve for something in a system, you have to use its square and its component. And most likely we have the z for in why z? Because z is take note in spherical components. We have this a simple value, no? So simplest value is z. So therefore, we use is z as the pivot of rotation. So therefore, we are very much interested to these operators. So since we have this operator, then we are now ready to find the eigenfunctions and eigenvalues. Okay? Eigenvalues, then after that, eigenfunctions. So you have to recall your linear algebra on how to do it. Okay? So the ladder operator also, but the ladder operator, raising and lowering are not Hermitian, of course. No? You cannot interchange from one position to another because they are not Hermitian. So there's a specific uh, rules of that. Okay, so that's all for today. Thank you for watching.